Yes, I come with.
Today. Okay, I did. All right. Please make sure that you don't lose the attendance sheet. Don't take it with you.
Too late.
Somebody took it already.
First we took it, then somebody else took it.
Just don't take it home.
Somebody took it home
Well,
last time.
sometimes some people put the attendance sheet into their bag and take it home. So try not to take the attendance sheet home, please.
You remember last semester for how many weeks?
Okay, the attendance paper I hope is somewhere. So these papers are from last week, so these are only extra papers. If you were here last week, then you have them. This is simply leftover papers from last week. It's very funny because Math 1 people have been stealing my Math 1 materials. Most of my metrics stuff is gone. And vectors, it's very, very strange. It's really very, very strange. But okay, I should feel flattered that somebody wants my mathematics. Okay. So we did all kinds of substitution, but I'm not really sure how far you got because there were, well, maybe 2-3 people asking me questions about substitution, and the rest
Can you just explain again
seemed so happy. Which part?
14?
14. Let me find it. If I still have anything
That
left.
version of it.
If I still have anything left.
I have here.
Let's see. Okay. Our combined 14. Tangent to the fifth. And not 10, and not 12, and not 13.
No.
No.
The other is just okay.
14. Alright. So number 14 from last time. Because, well, I know I did it, but well, there are different possibilities. So we have this tangent to the fifth power of x dx. Okay, that's great. So if we take t, the substitution equal to tangent x, then of course we can find the differential dt would be the derivative of tangent 1 over cosine squared dx.
Oh, cosine.
Right. 1 over cosine x squared, by the way, equals to tangent squared plus 1. So 1 over cosine squared x by the basic formulas is tangent squared x plus 1. So it's actually t squared plus 1. So now we can see what's going on here. This is one method. There are at least 3 different ways of doing this. I did it one way. I can do it another way here.
It's 1 over this one.
No.
dt. Okay. I thought dx. No, I don't know.
It is.
But we have dx there.
Yes. We have dx there. So actually, if I want to put dt there, then I should obviously, I would like to divide by cosine squared x. So then I would have this part would be dt, and this means that I have to multiply also by cosine squared x. So this is tangent to the fifth x times cosine squared x. Now this is dt, this is t to the fifth. Cosine squared of x is, if we turn this upside down, now we do have 1 plus tangent squared of x. So I can rewrite this tangent to the fifth of x divided by 1 plus tangent squared x, and this is already dt. So what I have is t to the fifth dt over 1 plus t squared, for example. Now what I can do is I can divide out a polynomial. So I could try to divide t to the fifth divided by 1 plus t squared and try to think what it might be. We could do long division, for example.
Yeah.
We could do long division, for instance. So that will be t cubed, so I would need plus t cubed minus t cubed. Then it would be minus just t. Okay, I've not enough space for this. Minus t, that would be this, so I need minus t plus t. That would be this part, so plus t over 1 plus t squared. I think it's something like this. Should be. I'm just dividing t to the fifth by 1 plus t squared. So this is integral t cubed minus t plus t over 1 plus t squared dt. The first part is t to the fourth over 4. Don't we have tangent to the fourth over 4 in the answer? Minus t squared over 3. Plus, now if I do this, if I multiply by 2 and then I divide by 2, then I have 1/2 natural logarithm of 1 plus t squared. And replace t by tangent and you have the answer. So one way of doing number 14, which is why it's the last example actually, because it is the most difficult, I think. So one way of doing this is actually focus on tangent, replace tangent, substitute tangent by t, and change everything in terms of t, of tangent. And actually cosine squared is easily changed in terms of tangent. If you know that one of the basic identities, turn it upside down, and you can actually replace cosine squared.
It is plus, as I said.
Which is plus?
Plus 1/2 of natural logarithm.
Oh, you said it's plus and I said in my answer it was minus.
Yeah.
Okay, then it's a mistake there. Okay. It is plus. This is one way of doing this. So, yes, you should know this. You should know that tangent squared of x plus 1 equals 1 over cosine squared of x. This is directly obtained from the first Pythagorean identity. This is one of the basic things. So you should be able to express tangent square in terms of cosine square in terms of tangent square, trigonometrically, not just by calculus methods, by derivatives and so on and so on. Which is actually also interesting because this is also the derivative of the tangent. So it can be used sometimes. Another method of dealing with this tangent to the fifth is actually, for example, writing it's sine to the fifth x over cosine to the fifth x. And for example, we could change everything into cosine. So I could write sine to the fourth x, sine x, cosine to the fifth x, and if I want to integrate it, then this is d of cosine with opposite sign, of course, because the cosine derivative is minus sine. So I could do it this way just as well. So I can do cosine to the fifth x. Sine to the fourth would be 1 minus cosine squared. That's sine squared. This part. Then if I square this, I have sine to the fourth d of cosine. And I can do this algebraically again. I can turn it in terms of t or in terms of u, whatever, I can denote t is cosine of x, and then I have a rational function, or u perhaps. Okay, if u equals cosine, then I can have an integral 1 minus 2u plus, u squared, u fourth, u to the fifth, du, and I can split it into 3 separate terms and integrate it like that. In this way, I would have the answer expressed in terms of u, which means in terms of cosine. In this case. In this case, my answer would not be expressed in terms of tangent, but it would be expressed in terms of cosine. And obviously there would be something like natural logarithm of cosine, obviously, would be there, because it's u to the power minus 1. This is 1 over u. This term would be, so I would have natural logarithm of cosine, which is interesting enough, because here I have natural logarithm of 1 plus tangent squared, but it can be explained in this, in these terms. It can be explained using these formulas. They will be exactly the same, because tangent square and 1 over cosine square can be converted each into the other. This solution of this one, it's not finished. I'm not going to finish it there. The solution in terms of cosine can be converted into this solution in terms of tangent. They are equivalent solutions.
Yeah.
The difference might be some constant term, term for this. But basically, if I do this integration to the end and compare it to this answer, in terms of tangent, in terms of cosine, it is possible to verify that these are basically the same thing. They both are exactly the same thing. They can be converted one into the other. So 2 different methods, but actually there are more possibilities. There are more methods with a little bit of inventive thinking, some more inventive perhaps substitutions. There is a universal trigonometric substitution as well, which I'm not showing to you, but perhaps so. The universal trigonometric substitution is x is substituted by tangent of some half angle, and then you can actually express many things in terms of t.
Yeah.
So that's the universal substitution that can be used even for non-trigonometric integrals, but that's used only when you can't do anything else, because in the end this universal substitution might give you a complicated integral. A rational function, but still quite complicated. Okay, so this solution is based on division of t to the fifth by 1 to t squared, 1 plus t squared. So if you know how to do the long division of polynomials, then this is okay. If not, then this part might be a bit tricky. Then doing it like this is perhaps easier. Because when we have sine to an odd power, we can always split off sine x, simply sine x, and the remaining part is sine to an even power. And if you have sine to an even power, then you can actually use something like this.
The question is sine x dx. Why it's not minus the cosine?
Because I forgot the minus. Right. Because I forgot the minus. So minus should come here. This is minus, and minus. And this would be, of course, minus whatever we get there. Yes, thank you. Thank you. I was thinking about it and I just started talking about something else and it flew out of my head. Right. Okay, so this was probably the most difficult of all these examples.
I'm confused.
And to finish this correctly, yes, as I said,
I just don't understand.
you have to be able to divide these simply to separate, to divide out the polynomial and leave it with a proper fraction. You know that a fraction is called proper if the numerator is less than the denominator, at least with numbers. And the fraction is improper if the numerator is equal to or greater than the denominator. For example, 5/4 is improper, 3/4 is proper. And the same applies to polynomials and rational functions. If the power of the numerator is less than the power of the denominator, then the fraction is proper, and proper fractions can be integrated easily, or perhaps not so easily, but that's for next week. And improper fractions need to be simplified first. We need to divide out the, well, with numbers we need to divide out the integer. With rational functions we need to divide out the polynomial. We will talk about proper and improper rational functions later, next week I think. I don't think you will be ready to do that on Thursday. The first test is not this week and not next week, but the week after that. It will be either on the 24th or the 26th of February. I'm not sure which. I will be able to tell you next week because I need to see how we are moving on, how well you are doing. But actually, I would like to do it rather earlier than later because we don't have much time and we do have a lot of material to cover. Yeah.
Will be this kind of
Yeah.
Tangent to the fifth?
Yeah.
No.
and will the integrals like natural logarithms and squares or tangent?
Yes.
Okay.
Integration by parts. That's the topic for today. Integration by parts. Integration by parts. So how we can get the formula for integration by parts? First of all, we have to take a step or two steps or three steps back to derivatives and to remember the product rule, how to derive a product of two functions. So a product of two functions, the derivative of the product of two functions is first derived, second not derived, plus first derived, second, first not derived, second derived. If I multiply everything by dx, I can multiply by whatever I like. uv derivative dx equals u derivative dxv plus uv derivative dx. Why not? So what I did is multiply by dx, both sides. So now this becomes d of uv. This is du times v, and this is u times dv. Now if I integrate both sides, so now the next step is integrate both sides. Integral of d of uv equals integral d du. I simply wrote this product in the reversed order, it's still the same product, plus integral u dv. This integrating and finding the differential are usually inverse operations. So basically integral of the differential is the same old uv. That was one of the first properties of integrals, if you remember. Last week or the week before that. Yes. The first property, one of the first properties of integrals was integration and differentiation are usually inverse operations. So this is simply uv. This is simply uv actually. And so this is integral v du plus integral u dv. And now I'm simply expressing this term Integral of u dv is uv minus this v du integral. So what's the use? Just playing around with integrals, differentials, sums, differences. It just seems to be just playing around. So what use is this formula? So what? Does it make things simpler? Does it make things easier? It appears that yes, at least it gives us a method for integrating some kind of product. So the formula, the magic formula, this is really magic, magic. uv minus integral v du. Okay, remember that, well, if you see this, but we normally see this, usually we see this in the form u dv is v derivative dx is, and so on and so on. So you see, in this case, the functions u and v are not really related in any way. Previously, when we did substitution, when we did the principle of invariance of form of differential, these two functions that we saw in the integral, the product of two functions, they were somehow connected. For example, we had, yes, u derivative times f of u. We saw the composite function multiplied by the derivative of its internal function. We saw things like this, or we saw things that could be reduced to something like this. But you see, in this case, these two functions are somehow related. They are linked. In this case, it's just some function u, just some function v or v derivative, but they don't have to be linked in any other way. There's no composite. They're simply a product of two functions, and one of these two functions could be taken for the derivative of something else, pushed into the differential. We push it into the differential, and then we have this form, and then quite formally, we simply apply this formula. What happens is, if I have one function outside the differential, and the other is put inside the differential, so if I put this inside the differential, I get this, right? If I can put one of those two functions into the differential, I get integral in the form integral of u dv, differential of some other function. Then I can see that, oh, it turns out that, first of all, I can multiply these two functions without any integration, without any differentiation. Fine. And here, this is where the miracle happens. These two functions magically swap places. And the aim, of course, the aim is to acquire an integral easier to solve. This might look awful and difficult to solve, but if I see that if only these were reversed, I could do it. Then this works actually quite fine. Then there's no problem with this. So the first example, a simple one. Okay, I'm going to erase this because this is on the handout paper. This is on the material, so if you didn't hear me doing this, then it's just as good on the board as on the paper.
What's the video?
What about the video?
They can see it in the video.
Okay, they can see it. Alright, so let's do the first example. Let's integrate ln of x dx. We know how to derive ln, which is again a very interesting thing. We know how to derive ln, we don't know really how to integrate ln. And that's how we do this. This will be the u function and this will be the v function. So I have integral u dv. So I'll make some notes. So this will be the u function and this is this is dv. So x is v actually. So I apply that formula directly. I can write uv, okay, x times ln x, uv, x times ln x, minus integral v du. V is x, du is d of ln x. Now, all right, differential of ln x. Okay, I have to write my, draw my magical circle. Okay, I will write v. dv equals v derivative dx. Remember this. If I need to get a factor into the differential, I integrate. If I need to get a factor out of the differential, I derive. So this is the thing that's always on the board. For now, it won't be on the board during the test, but it's in your notes. Okay, so d of ln x is actually the derivative of ln, which is 1 over x, times dx. Now I see x ln x minus integral x, this becomes this, so times 1 over x dx. These two cancel each other out. I simply have to integrate 1, and the integral of 1 is simply x, and plus the constant of integration. So this is the integral of the logarithmic function. It appears that this integral of logarithmic function involves the logarithmic function itself. Surprisingly, or perhaps not so surprisingly, because the inverse of the logarithmic function is exponential, and you know that the integral of the exponential function also involves exponential function itself. So that's not a big surprise. But there are ways of doing this, let's say in as simple a manner as possible. So I simply showed you the first example just to illustrate that formula. Basically, we still have several things remaining. First of all, in which cases should we try to apply this formula? In what cases? What functions, what products are good for this method of integration? Secondly, how to set up this integration as efficiently as possible, as simply, so that we don't have to do too much writing, so that everything we write down is concise, correct, easy to use in your process of integration, and so on. So, first of all, some general notes for this. Generally, the types of functions that could be used as u or v are exponential functions, e to the power x, 2 to the power x, well, a to the power 2x, anything. So exponential functions might be one of the factors. Another thing could be trig functions, sine x, cosine 2x, perhaps tangent x, and so on. So trigonometric functions could be involved.
And arctangent.
That's not trigonometric really, but yes. Powers of x, x squared, x to the third, or perhaps, yes, perhaps x to the power minus 2 and so on. So powers of x. And then, yes, we could have logarithmic functions, ln of x, log at other bases of x, and so on, and arctangent or arcsine sometimes, arctangent of x, arcsine of x. Well, almost all the functions we have been looking at almost all the functions that we know. We don't know many more other functions. Roots, yeah, roots, but roots are powers. But we generally don't use roots in this method because both integrating and deriving radicals is, let's say, complicates things. It can be done, but for our examples, there's not like that. Okay, now the rules. So generally, what we will see in an integral that is to be solved by this method is a product of two functions, an integral of a product of two functions, and these two functions would generally be one of the two of these. For example, e to the power x times sine x, or x cubed times e to the power x, or x squared times cosine 2x, and so on and so on.
How about x to the x factor?
X to the x? Can you derive it? No. X to the power of x is special. Okay. This is not your basic elementary function actually, because x to the power x is not defined for all values of x. So it's you have to be very careful with that kind of function. But all right. So back to these. So generally you will see integrals in the form of something like x squared e to the power x dx, or x to the power 3 times cosine 2x dx, or perhaps e to the power 2x sine 3x dx, for example, like this. So how do we solve this kind of integrals? So two functions that are basically not related in any way at all. Then what we should do, we should assume that one of these functions is the derivative of something else and find that something else. If we say that, okay, one of these functions is v derivative, v prime, then we ask, what is v then? We decide what the v function should be from this. In other words, we integrate. That's why it's called integration by parts, or partial integration, because we integrate only one part of this product, only one factor. Surprisingly enough, to find du afterwards, we will have to derive. So in other words, the integral of a product of two functions is turned into a mixture of integration and differentiation. And the thing is, which one do we want to integrate and which one do we want to differentiate? So which will be u and which will be v? That's the general question. So there is, let's say, an unwritten rule, or unspoken usually, rule of thumb, at least for these simplest functions. If you have an exponential function, then this is the first candidate for v derivative. So this is the first candidate for v. So for doing this, the first candidate is exponential function, if it is there. If there is no exponential function, actually I have already written them in the correct order, that's what I usually do. If there is no exponential function, then this is the second candidate. So in this case, it means that in this case, e to the power x would be pushed into the differential. In this case, the cosine would be pushed into the differential. In this case, the exponential function again would be put into the differential. If there is no e to the power x exponential function, no trig function, only a combination of everything else, then this is the final candidate. Then we try to put the power into the differential. We never try to put this into the role of v, or v derivative. We don't do v for these functions. These stay outside, because it's always easier to derive these functions. The derivative of ln x is easy, it's 1 over x. It's much simpler than the one we got, the integral. The derivative of arctangent is 1 over 1 plus x squared. It's easy. Integrating arctangent can be done using this method similar to the natural logarithm, similar to my first example. But we do not try to make the v function out of these. No. So if I have a natural logarithm, I leave it outside, it's u, it's not v. So these functions are always the u functions. These functions might become the v functions. And now let's see, how can we write things down? How can we write things down to make it easier to solve this? Alright. X sine x dx. Alright, next example. X times sine x dx. My next example. So what I remember is that there's no exponential function. So no exponential function becomes the v function, but there's a trigonometric function, and this should be my v function. In other words, I would think this will be the u function and this will be dv. Again, this is simply a note. You don't have to do this always. I'm only going to do this sometimes for the first few examples. So now the serious part. The serious part that we are doing is, okay, so if the u function is x, then du, well, we will need du for the formula. I express du, it's the same, it's dx. Sometimes it's something else, it could be x squared or something else. So in that case, I need to find the differential in the correct way by deriving it. And this is why this function stays outside, but eventually it becomes, well, it gets derived. It's differentiated. So one of these is integrated and the other one, surprisingly, is differentiated, is derived. So now I see that dv is sine x dx, and to find v, actually I have to integrate this. This is the partial integral. I'm integrating only a part of this. So v can be found by integrating this. So, alright, you don't have to write, it's not always strictly necessary to write down this. That's why I put it in green, because I actually know that sine x is the derivative of my minus cosine. So v will be minus cosine x. No need for the constant. We don't need the constant of integration here. We will put the constant in the answer in the end. Okay, so you don't have to write this, but this is what happens. This is this partial integral, integrating by part, just one part of this. And now, when I have done all my inventory, well, this is what it is. It's taking inventory of what we have and what we can get. Now, all I have to do is simply mechanically follow the magical formula. So uv, u is this, v is this. uv is minus x cosine x. Minus the integral, the miracle happens, u and v swap places, v du, according to the formula. v minus cosine x, du is just dx this time. Sometimes it's more than just dx. You have to be careful, sometimes there's a lot more there. Alright, so it's minus x cosine x minus minus, I can change it into integral of cosine x dx, which is, no, just sine x, just sine x. The derivative of cosine is minus sine, but the integral of cosine is sine. The integral of sine is minus cosine. So we have minus x cosine x plus sine x plus constant, and that's the answer. And that's the answer. So this is why I call this method magic. The formula is really magical if you know what to do, if you know, let's say, if you know how to wave the magic wand. If you do this inventory, it means you don't have to do more transformations and integrations and whatnot later. You do it now, and then you have it all in front of you. What is u, what is du, what is dv, what is v, and you simply can put everything into the formula. Nothing else to do. So this is actually the most important part in this process. This is the most important part. And of course, yes, knowing how to integrate this. Naturally. Knowing how to integrate this. Sometimes constant factors are involved. For example, if we have sine of 3x, then of course in the process of integrating I have to divide by 3, for example. Or if I have x squared, then du will be 2x dx. Again, more things involved. Sometimes you may need to repeat the process. If this integral is indeed simpler than the original one, but it's still a product, you still need to apply the formula for a second time, so you have to repeat the process. Sometimes it happens. Let's have a look. All right. X squared sine x dx. No problem. X squared sine x dx. Okay, my inventory. Again, I know already by experience that this is the best u function and this should be the d function, the v function. Again, remembering that if we have this trigonometric function, no exponential function, then this is the best thing to do as the integral. In other words, powers are better to derive because deriving a power lowers the degree, lowers the power. So from x squared, by deriving it, I get just x. From an x cubed, by deriving, I get an x squared. It simply decreases the power. So x powers are better derived than integrated. It makes things simpler. So actually, u is the function for deriving and v is the function for integrating. And so u is x squared, and in this case du is 2x dx, according to this, of course. If I have to find the differential of a function, I have to use the derivative of this. Now, again the same. dv is sine x dx. Never ever, you must never forget dx. dx, dv, du, you see they are important in this formula. They are extremely important in this formula. Never lose them. So v is the integral of this. By now I know it's minus cosine x. If I integrate sine, I get minus cosine, as I did there. So now I have uv minus x squared cosine x minus integral v du. V du. Oh, not so very pleasant now. V du. First of all, I can take 2 outside and I can take this minus outside the integral. So actually, when you get used to this method, you start taking constant factors and minus signs outside to simplify things. And now I only have x cosine x dx. Now I have only this. Because I took 2 outside and took this minus outside to make this.
One more inside.
And yes, and now I have to do it again. So now, this time, well, formally, I should use other letters, I should use other variables, because u will be different now, it's not the same. So mathematically, it would not be correct. I could use a and b or alpha, beta, or something. Yes, we could. So formally, I should do that. Otherwise, it becomes, but then I have to rewrite that formula using those new variables. It's too complicated. So, okay, so this is simply the first time, this is the second time, so not to confuse things. U is x, du is dx, but it's not the same u as there, so that's why I'm putting 2 there, to make the distinction, because renaming the variables can be messy. Sometimes more opportunity to get things confused and wrong than otherwise. dv is now cosine x dx, so v should be the integral of this.
Sine x.
Okay, but the integral of cosine is sine x. Okay, so you don't have to write the integration here, or you can. You can do this. I wrote it in the first example. I'm not writing it again. So now we have, and again, it's good to write things below each other so that you can follow what's going on. So I'm simply copying this, minus x squared cosine x plus 2 times. Now this integral has to be resolved using this. uv x sine x sine x, minus integral v du. Aha, sine x dx. And now finally I'm writing it below again. So it's minus x squared cosine x plus 2x sine x minus 2, because this 2 applies to the integral as well. The integral of sine x is minus cosine, so I have to remember, because I integrate this, the integral of sine is minus cosine, so I have to change the sign because of integration. Cosine x, and that's all, plus c. That's all. That's all. Oh my God, is it so terrible?
No.
Is it so very terrible?
When it is solved, great.
So if you have x cubed, then you would have
Sine 2x.
4 terms. Sine 2x, that would mean extra factors.
Yeah.
Should we do that with some extra factors? We can.
It is an exercise.
Yeah, it is.
In exercises.
Numbers,
All right.
numbers.
So for now, I want to stop before example 4, because that's something that perhaps should be discussed on Thursday. So focus today on the exercises. So we should do from 1 through 12. From 1 through 12 is the good part of the exercise today.
For individual?
From 1 through 12, yes. Because, by the way, some of these exercises will repeat the examples, so we can skip those. I didn't take out the exercises that I have used as examples. Can you show the 7th one? 7 already. Skip ahead. All right, number 7. And then I'll return, then I'll go back to something like number 4, perhaps, where there's cosine 2x, and then number 10, perhaps, but all right, number 7. So it's natural logarithm of x squared dx. Now let's remember, first of all, this is a composite function. Secondly, it's not a product. It's not in that form. It's not a product. But it could be, third thing to remember, we do not put logarithm into the v function. So this logarithm squared, all of it, is the u function. And the v function is x. Simply that. So the first thing to remember is several things to notice. No product. Composite function, we didn't deal with composite functions there. And yes, ln x is not the thing that we choose for v. So what we have here is that this is u and this is dv already, without any change. Without any change. All we have to do is, of course, if u equals ln x squared, then we have to write du is 2 ln x, chain rule, times 1 over x dx. Differentiate by chain rule. If dx is dv, so dv is dx, it means that v is simply x. Alright, uv, x times ln squared, uv, according to the formula, x times ln squared of x. Easier to write it like this than this, it means the same thing. But I put it like this so that people do not get too confused. Minus integral v du.
The first one is
X times du is this. So it's, okay, I'm putting 2 on the side. Ln x, 1 over x, dx. Okay. Some nice magic happening now. X x and 1 over x, cancelling out. So now we have integral of ln x. So we have x ln squared x minus 2 integrals of ln x dx. And this is where you have to remember what was the first thing we integrated by the formula. It was just this. It was just this. We can repeat it, or you can repeat it, or we can just put whatever we got there, put it there. So what we have is x ln squared x minus 2 times. Anyone remember? X ln x minus x. Or finally x ln squared x minus 2x ln x plus 2x plus c. Is the final answer for this. So for this integral, I simply used what we obtained in the first example. We did this integral just after I gave you the formula. So basically ln of x is never pushed into u, and arctangent of x is never pushed into v. They are always u, and sometimes you have to repeat the process twice. For example, here, if we had not done ln x in the first part of the lecture, then I would have to do this process again to obtain this. But because we already have integral of ln x, I simply put it in there. Because we already did it today. Okay? And what else? X times e to the power x is too simple.
The homework number 5.
Homework number 5. No, that's for next time.
Okay.
That's for next time.
It's scary.
It's scary. It's for the next time. It's for the next time. Don't worry. Don't worry. Alright, we could, so arctangent can be done similarly to natural logarithm, so I'm not doing it now because some people might want to try it for themselves. 10? 10. Okay. 10 is slightly more difficult than number 9, very similar. But alright, number 10. Number 10. Integral x squared e to the power minus 2x dx. So, we remember that exponential function is the first candidate for the v function. So this is dv and this is u. Again, you don't have to mark this. I'm simply showing this for your sake so that it's easier to understand what we are doing there. So u is the function x squared, which means du is 2x dx, never lose dx. E to the power minus 2x dx is dv, and by integrating we get v is the same exponential function divided by minus 2. So it's okay, like this. So it's minus e to the power minus 2x divided by 2. By integrating, remember that when you integrate and you have this numerical factor, you have to divide by it. This was one of the first rules. So if you integrate a function of a linear function, dx, primitive function kx plus b plus constant, but you have to divide by that constant k. So because I have minus 2x, I have to divide by minus 2 when I integrate. That was one of the first rules. Okay. Now, uv. So minus x squared e to the power minus 2x divided by 2 minus integral v du. Alright. Now, minus in the integral, I can put it there. So this minus actually makes this a plus. What I do in green is simply showing you what I do. Now, v du. Multiply by 2, divide by 2. These 2 and 2 will cancel each other out. But I can write them, okay, multiplied by 2, divided by 2. So this is 1 and this is the other. So what we have inside the integral, is e to the power minus 2x times x dx. And what happens now is that we have to repeat the process again. But fortunately now we see that power has been reduced. But one more time. So this was the first time and this will be the second time we do this. Again, now this time u function is simply x. No more x squared there. Simply x. So du is dx now. The v function is obviously the same. So I can write v is minus e to the power minus 2x over 2. Simply because it's the same. Now what we have is minus x squared e to the power minus 2x over 2 plus, now uv, again negative. So it will be again minus. So because this was plus, now we have another minus. It's again minus because of this. Because this was before we did this. This took this minus sign and made it positive. Now we have another one in the v function. So, well, yes, okay. I can write minus like this in the brackets, why not? To make things easier. uv, so it will be x times e to the power minus 2x divided by 2. Okay, again division by 2. Minus integral v du, this, so minus 1/2 makes it plus 1/2 there. It's simply e to the power minus 2x dx. So now what we have is minus x squared e to the power minus 2x over 2 minus x e to the power minus 2x over 2. And finally, plus, but when you integrate and divide by minus 2, remember, you have to divide by minus 2 when you integrate. So plus, but divide by minus 2 becomes minus division by 4. Because 1/2 is there and 1/2 happens from this e to the power minus 2x. You may put it on the, or put everything on the same line, or you might not. That's whatever you like, there's no need. You don't have to put everything on the same line. You don't have to take e to the power minus 2x outside. If you like, you can. It might make things simpler. You could do minus e to the power minus 2x over 4, and then you have 2x squared plus 2x minus plus 1 in the brackets plus c. You can do it something like this, somewhat like this if you like. Not strictly necessary. I can read this more easily. I can understand what you have been doing from this more easily than from this. So there's no really any need to do this, but if you like, of course you may, because this does look nicer. This does look nicer. In this form though, it's easier for me to see what you have been doing, and perhaps the most common mistakes. The first most common mistake is confusion with signs. You lose minuses, you change minuses into pluses, pluses into minuses without any real reasoning, just something. So a mess with signs. The second most common mistake, forgetting to divide by the constant k, by the coefficient k. Third most common mistake, forgetting to integrate. simply taking this for v. But basically it is, as I said, this is the most important part of all. This, of course, I've been juggling a little bit. I've been trying to make things go faster and simpler. But in fact, you can leave minus here, minus in here, multiply by 2 in here from this, divide by 2 there, but from this, leave it inside the integral, simplify slowly. No problem with that. No problem with that. This is not a very complicated method when you get used to it. I can understand that at first sight it might seem horrible. It did to me when I first saw this. But on the other hand, if you do it very, very carefully, and most of all slowly, using brackets, not losing constants, not losing factors, not losing minuses, but this is the greatest danger actually. Most people can integrate things like e to the power x, or sine x, or cosine x, or even x, or x squared. But the problem is, the tricky part is this: where do we change the sign? Where do we divide by some number? Where do we multiply by number? Sometimes you have to multiply by one number, but divide by something else. Multiply by 3, divide by 2. It depends on what you have in the functions. So this was number 10.
About this process, we should do this process after we get just x for u, or
Sometimes we get, until we get just x for u, yes, until we get just x for u. Basically until we get a simple function inside the integral, something that you can integrate easily. Something that you can integrate easily. So notice please that with the power of x, all we have been doing is derive. We never integrate this part. We derive this part, then we have x. We derive this part, we never integrate it. So the u function always gets derived. And this other function, the one that's v derivative, gets integrated. Which is a little bit, it seems a little bit strange, but this method actually works. Next time I will show you how this method can be used for simpler integrals as well. Alright, so which integral should I do for you now? In number 12, you need to repeat the process 3 times.
Yeah.
And it has the factor 2, which means you will have to divide by 2, divide by 2, divide by 2.
What about homework number 2?
Homework number 2, ln x divided by x squared. Okay, because
Not so hard.
no, it's not so hard if you remember that it's 1 over x squared that has to become v. If you remember that ln x never ever goes into v, then it's easy. Alright, so we have ln x divided by x squared dx, which is actually x to the power minus 2 ln x dx. And now we have a product, and now we have to remember ln x never becomes v, so ln x must be u. So this is the u function, and this is the v derivative. Taken with dx, it will form dv. Alright, so if u is ln x, then du is 1 over x dx. We will use it. Now, if v derivative is x to the power minus 2, then v itself is this integrated. By integrating, when we integrate, we add 1 to the exponent and divide by the new exponent. So it would be x to the power minus 1 over minus 1, or minus 1 over x. This. Again, it's important to write it into an easily recognizable form. In this form, it's difficult to understand what's going on there. It's important to change it into the nice form, into the form that we can use. And so uv ln x over, minus, so uv minus ln x over x, minus ln x over x, minus integral v du. Minus 1 over x times 1 over x dx. No more logarithms, only a power, easy to integrate. So it's minus ln x over x plus integral of minus minus, that's one plus, x to the power minus 2 dx. We just did x to the power minus 2. We just did integrate it, so we know what to write now. So it's minus ln x over x, and it's this. So it's minus 1 over x plus c. So yes, it's not so difficult. It looks something strange, oh no, we don't know how to do this kind of thing. So remember that division by x squared means simply x to the power minus 2. That ln x can only be the u function, not the v function. So there are some things to memorize. Indeed, the best order of integration, the best order in which to use the functions u and v. And not forgetting the signs, not forgetting the divisors, the denominators, numbers, and, well, it looks worse than it actually is. Okay, now what, 12? Or...
What is a graphic integral?
What? Graphic integral? Why do you want it? You don't know. We'll see the geometrical interpretation soon. Well, such thing as simply graphic integral.
18.
18?
Yeah. Which one?
18.
For you or?
18 is, well, 18 is simple. Cosine divided by cosine divided by sine is cotangent. Cotangent, but the derivative of cotangent is 1 over sine squared. So we actually have cotangent times cotangent derived, or we could remember that cosine is the derivative of sine, and we have sine to the power minus 3 there. That is actually not so difficult, and it's somehow it's actually out of place among those. It stands separately. 19. Ooh. It can be grouped with those that we will discuss on Thursday. It's repeated, and then it reverts back into itself. So this is where you have to solve some kind of equation in the end. This is again one of those. This is of a similar kind to e to the power x cosine x, which is something that we have to talk about separately. Or, well, we can look at that other part. In fact, so it's up to you. We can do something like 13. We can move on. Or my example number 4. Okay, e to the power x sine x dx. This will be the integral where we repeat the process and then we think, oh no, we are stuck. But we are not really stuck. So for this, we remember that this will be the first v function, this will be v derivative, and this will be the u function. Because e to the power x exponential function is always the first to be used as v. And so u is sine x, du is cosine x dx, v derivative is e to the power x, which means the v function is e to the power x. Fortunately, simple. And now uv, so it's e to the power x times sine x minus integral v du, e to the power x cosine x dx. Now we do the same again. So this was the first time, and this is the second time that we do this. Now this time, u is cosine x, and du is minus sine x dx, but v is still e to the power x, because the rule is still the same. So we have e to the power x sine x minus, brackets, uv e to the power x cosine x minus integral v du, which is e to the power x times minus sine, which means I have to change it into plus. Now when I open the brackets, I have e to the power x sine x minus e to the power x cosine x minus integral e to the power x sine x dx, which is where we think, wait, this is what we had at the beginning. Sometimes it happens. Now, one thing that saves us is this is integral, but this is minus the same integral. If we had plus the same integral, they would cancel out and say, what? Is this equal to 0 then? But because this is minus, we could say, okay, this is integral I, and this is expression minus the integral I. So I imagine an equation like I equals e to the power x sine x minus cosine x minus I again. So I can carry this integral over to the left-hand side, get 2I equals this.
And then divide by 2.
Yes. So 2I is e to the power x sine x minus cosine x. Well, probably it's time to write the constant of integration, but we can do it now. So integral I, the original integral, this actually is e to the power x sine x minus cosine x over 2 plus the constant. So this is slightly unusual. Well, it's quite a common thing for this method. It happens. It happens, especially where you have exponential functions mixed with trigonometric functions. Especially in situations like this, it happens. It's perhaps it's a little bit unusual and unexpected for the first time when you see this. So because this integral, well, it's cyclic, of course. Because the derivative of exponential function and the integral of the exponential function is itself, and because the derivative and integral of sine and cosine is cosine and sine, so of course there's a cycle going on, the repetitions going on. It cannot be avoided. But if everything is done correctly, then the integrals will never cancel out. They will never disappear. You might have some constants here sometimes, plus, for example, 2 such integrals. You can still carry it over to the left-hand side and express it using this, the rest, the remainder of that integral, everything else. So this is, and now if you ask about homework number 5, for example, or number 19, the same thing happens there. Exactly the same thing. The function looks very different, but if you remember that ln of x, ln of anything has to stay outside of the differential, and you proceed with integration and applying this method, you will come to a situation like this again. So this is an interesting side effect of this method. If I had 2 here, I would have 3 on the left-hand side, and I would divide by 3. Because I can take this integral over to the left-hand side, I simply combine two identical integrals are combined And then, of course, to get a simple integral, I have to divide by 2. So this is an interesting twist on this method. An interesting twist. Well, what makes it more complicated probably is the involvement of constants. The involvement of various constants. The constant could be in the power e to the power 3x sine 2x, and then you have to manipulate those numbers correctly. For example, so number 14, we could try number 14 or 14 or 19. Which one? 19. Oh, right, 19. Cosine x, ln of sine x dx. So, composite function, ln of sine, it's a composite, which means it's basically ln. We have to look at ln. So, ln is left outside. So, this is, by all means, it's the u function, because it's ln of whatever. ln of whatever is always u. So, this is v derivative, obviously. Alright, so if u is ln of sine x, then du is, to derive this, ln derived is 1 over sine x times sine derived is cosine x dx, which is actually cotangent. Which is actually cotangent of x dx. Cosine of x, so that's v derivative, so which means v itself is sine x. Or perhaps it won't do that. Can't remember, perhaps I got confused a little bit. Well, we'll see. We'll see. So now uv, so it's sine x times ln of sine x minus integral du sine x times ln of cotangent. That's actually it's more simple than I thought. Times cotangent dx. Sine times cotangent actually is simply cosine. This is cosine. So it's actually easier. It's simpler than I thought. It's simpler than I thought. I had forgotten this. So sine x ln sine x minus integral of cosine, which is sine. Easier than the previous integrals. Even though it's number 19 and looks horrible, it looks horrible at the beginning when you look at this. But if you set up things correctly, if you take your inventory and if you remember that ln can only be u function, okay? Everything else works out very nicely. So I can only repeat what I did, what I said 2 or 3 times today. This is the most important part, to set things up correctly. Because after this, all you have to do is copy them into the formula. You have the formula in front of you, you have done the inventory, you simply take these things and put them into the formula. And then you see what can be simplified, how can you simplify the signs, how can you simplify the factors, the constants, and then is this integral simple enough to integrate, or should I do it again?
Plus?
Number 18.
It's plus, no?
D prime, cosine, this?
Plus.
Yes, because this is the z. Cosine dx.
If v is
u
minus,
dv. To get this. To get this. I wrote v prime because cosine was not directly by the side of dx. If I had ln sin x times cosine x, if I had the reversed order, then I would write dv including this. But because they are separated, I wrote v prime, not dv.
Can I ask
These two together make dv. More questions?
It's not plus sin x because it's minus sin x, and we have a minus and it's plus, or I'm wrong? And they
Wait,
sin x times cot x,
here?
they are cos x, right?
Yes, it's cosine.
Cos x dx,
Yes.
and this is not minus sin x, or
No.
this is sin x.
No. Because when you differentiate, when you derive cosine, you get minus sign.
Yeah.
But when you integrate cosine, you get plus sign. The signs don't change, it's still minus. It's still the same sign. Because the derivative of sine is cosine.
Yeah.
But the integral of sine is minus cosine. Derivative of cosine is minus sine, integral of cosine is plus sine. So that's very easy to get confused there. If you don't know this very well, if you haven't been doing mathematics for 30 years, then you might forget these things sometimes. It's understandable, but come on, you are young, you have a better memory than I do.
In that this sine of x times what's cosine?
It's cotangent. This is cotangent because it's this. It's this. Yes, this is this. Cotangent.
Can you possibly use the ION something just in general? The ION x vis-a-vis.
In general.
We reach the result of
Well, if you can remember, then yes. Obviously, I will not ask you to do that in the test to integrate ln of x. So if you can remember it by heart as a standard integral, yes, you may.